In this chapter, we will be exploring the concepts of permutations and combinations. In this lesson, we will be introducing the fundamental counting theorem.
So the fundamental counting principle is actually something that is fairly intuitive. Okay, I think most of us, when kind of confronted with a problem like you're going to see in just a few minutes here, even without knowing the fundamental counting principle, you would very likely have answered the question correctly without any kind of prompting here. Basically what it says here is that if you've got a task, one task that can be performed in A ways, and a second task that can be performed in B ways, okay, then the two tasks can be performed together in A multiplied by B ways. In other words, we're going to multiply those options together. So if you think about it like this, let's say you've got, I don't know, just make it really easy. Let's say you've got 3 pairs of pants, okay, and you've got, let's say, 5 shirts, okay, 3 pairs of pants and 5 shirts. The question is, how many outfits is this? Okay, well, to get an outfit together, you need to put on a pair of pants and you need to put on a shirt here. Now, how many different ways could you put on a pair of pants? Well, there's 3 different ways you could do it. How many ways could you put on a shirt? Well, there's 5 different ways you can do it for a total of 15 different options here. Now, we're going to look at an example of a question here in just a second that will make that maybe a little clearer if it's not already clear to you. But I want to just focus on this right now. In order to answer this question, I have to look at the number of options in terms of the way these things can happen here. I want you to know that this 3 represents a single choice out of 3 options. Good. So the 3 represents the number of options, okay, not the number of things you're choosing. I'm only choosing one, just 3 options here. Just like the 5 represents 5 options. I'm only choosing 1 pair of pants, okay? So it's not that I'm choosing 5 of them, I'm only choosing 1. That number all by itself represents 1 choice out of a group of 5. Now, I emphasize that because in a little while in this chapter, something's going to be introduced that's going to put this into confusion here, what we're doing. Okay, so I really want you to be clear on what that number represents. It's the number of options, but you're only making 1 choice here. Now let's take a look at an example that might help clarify this a little bit more.
A school cafeteria offers sandwiches made with fillings of ham, turkey, cheese, and egg. These can be put on white, multigrain, or rye bread. How many different sandwiches can be made using only 1 filling?
Well, the first way we could answer this question is to use a tree diagram. And I think this is a wonderful tool for us to be using. It's absolutely fantastic because it really, really clearly illustrates the relationship that the fundamental counting principle is trying to articulate here. So we're going to complete this following diagram here. So here's kind of you at the beginning here, and you're going to make a sandwich. Now, to make that sandwich, you've got 2 different tasks you need to accomplish. You need to choose the filling and you need to choose the type of bread here. Okay? So you've got 4 choices here, and then every time you make a choice, you now have 3 options after that choice here. So this is what we mean by filling this in here. You could have a ham on white, a ham on multigrain, and a ham on rye. We could have a turkey on white, turkey on multigrain, turkey on rye. We could have a cheese on white, cheese on multigrain, cheese on rye. We could have an egg, whoops, I wanted to spell egg. We could have an egg on white, an egg on multigrain, and an egg on rye. Okay, so each choice of filling here then leads to choices for the types of bread. Now you can count this all up here. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so there are 12 different sandwiches that you could create here, okay? 12 sandwiches. Now, let's take a look at how the fundamental counting principle would have applied here. So the type of sandwich, in other words, what's the filling going to be? Well, we've got 4 choices there. Okay, and remember that 4 represents a choice of 1 object out of 4. I'm not choosing all 4 fillings here, I'm just choosing 1. And then I have to choose 1 type of bread here, and that's 3 options there for a total of 12 possibilities. Okay, that's how the fundamental theorem, the fundamental counting principle works. Okay, now obviously you can see that the fundamental counting principle is a lot more efficient than the tree diagram. The tree diagram does a great job of illustrating the relationship here. From this point on, though, we want to use the fundamental accounting principle. We want to do this as efficiently as possible and not waste time with models like this. However, there will be times later on where applying the tree diagram is actually the best idea. But we'll see that in a bit. Let's continue to look at some more examples.
A toy manufacturer makes a wooden toy in 3 parts. Part 1, the top may be colored red, white, or blue. Part 2, the middle may be orange or black. Part 3, the bottom may be yellow, green, pink, or purple. Determine how many different colored toys can be produced using the fundamental accounting principle.
Okay, well, to answer this question, we got to realize that there are 3 different tasks required of us. Okay, we got to choose the top, we got to choose the middle, and then we got to choose the bottom here. Okay, those are the 3 tasks here. Now, how many ways can I complete the initial task choosing the top here? Well, it can be colored red, white, or blue. That's 3 options there. Okay, 3 options. I'm only choosing one. 3 options. Okay, the middle could be orange or black. That's just the 2 options. Okay, whoops. Sorry, I gotta hold that. That's just the 2 options there. And then the bottom could be yellow, green, pink, or purple. Okay, there are 4 options for that. Now, multiplying these all together, and at this point right now, we're going to take a quick moment here just to discuss the multiplication here and a bit of vocabulary here. One of the ways that you can tell that we're multiplying here is because of the word and. Okay, we're gonna link multiplication. Okay, we're gonna link multiplication with the word and, because for me to complete this task, or this overall task, I should say, I've got 3 subtasks I need to complete. I need to choose the top and a middle and a bottom. Okay, in order for this whole thing to be complete, all 3 of those have to be in place. Okay, now altogether that's going to be 24 different toys that we can create. Okay, 24 different color patterns there. Okay, but again, remember, multiplication we're going to link with the word and. And so in fact, sometimes if you're getting stuck and you're wondering, oh my gosh, what should I do here? How do I handle this problem? In a lot of cases, if you just kind of took a moment, paused, and talked through the problem in your head, you would hear exactly what you need to do. Pay attention in your own description to the use of the word and.
Colleen has 6 blouses, 4 skirts, and 4 pairs of shoes. How many different outfits can she choose from, assuming that she wears 3 items at once?
Oh, well, it looks like I should have looked ahead before I used that initial outfit example here. So Colleen's got 6 blouses to choose from, 4 skirts, and 4 pairs of shoes. So a complete outfit here is going to consist of 3 different parts: the blouse, the skirt, the shoes here. So what I'm doing by drawing these lines down here, this is not just placeholders or fill in the blanks for us. What I'm doing here is identifying the tasks that I need to complete here. When I put the 3 little lines here, I'm implying that there are 3 separate tasks that need to be completed, or subtasks. This whole thing represents one task. These are the 3 subtasks. This first one is going to be the choice of blouse. This will be skirt, and this will be shoe. Now, there are 6 options here, so 6 multiplied by, there are 4 options for the skirt and 4 options for the pairs of shoes. So I need a blouse and a skirt and a pair of shoes here. Again, each number on its own represents the number of options, but I'm only choosing one, okay, from each of those. And when you multiply those all together, you're going to get 96 outfits. Okay? There are 96 different ways that these can be put together to form an outfit.
The final score in a soccer game is 5-4 for Team A. How many different halftime scores are possible?
Here's an example of a question that really gets to the heart of what makes this chapter a high school level concept. Because you think about it, up to this point here, all we're doing is multiplying. That's it. We're just multiplying numbers together. I mean, this could have been introduced much earlier in your education. Except that a question like this requires you to really look at this and think hard about what is being said here, okay? The final score in a soccer game, we have already talked about, this is 5-4 for Team A. Okay, so Team A wins. How many different halftime scores are possible then? Okay, well, what I got to do is I got to figure out basically the total score that could have existed at halftime, where this is, let's say, Team A and this is Team B. thing is, how many different options are there for the number of different goals that A could have scored by halftime? It is very tempting to look at this and say, well, there's 5 options for A, 4 options for B, 20 total. But that's incorrect. Okay, that's not correct here because you're not thinking this thing through entirely here. Okay, how many different scores or how many different sums of goals could they have, like total? By the end of the first half there, well, the answer is it could have been 6. There's 6 different options for A, and there are 5 different options for B. Let's take a look at it. They could have scored, by the end of the first half here, A could have scored all 5 of their points, 4 of their points, 3 of their points, 2 of their points, 1 of their points, or they might not have scored any of those points in the first half. That's 6 different possibilities. Just like for Team B, they might have scored all 4 of their points in the first half, 3 of their points, 2 of their points, or just 1 of their points. Or they might not have scored any of those points in the first half. So you have to consider that option where they didn't score anything here. So there's 6 different ways that we could get points for Team A, 5 different ways for B. There are 30 different scores for that halftime.
How many different arrangements can be made from the letters of the word cat if no letter can be used more than once?
Okay, now this is a really common problem, by the way, to take letters in a word and ask about how many different ways you can arrange them. And we're not talking, when we talk about creating words from this, they don't have to have any meaning whatsoever. We're basically just talking about the arrangements of letters. It's important to note this, and even though this question has said it, okay, this question says if no letter can be used more than once, okay, there's no repetition allowed here. That is an assumption you should make here. You need to assume that if you use letters from a word, okay, no repetition is allowed. Okay, now there are other contexts here when we're going to be talking about letters where repetition is possible. For example, if we're coming up with a license plate, you can totally repeat letters in a license plate. But if we're talking about letters from a word, then you have to assume that repetition is not allowed. Okay? So, in this case right here, we're talking about the letters in the word cat. So, I've got 3 tasks to perform. I've got to choose the first letter, okay, the second letter, and then the third letter. Now, for this first letter here, there's 3 letters in the word cat, so there's going to be 3 options here. Once I've chosen one, that leaves me with 2 letters left over to choose from. And then once that's done, I really have no option for that last one. And that's altogether, that's going to be 6. Now, in this particular case here, because the number of options here is relatively small, I could actually show you all of these. It could have been CAT, CTA, ATC, ACT, TAC, TCA. And those are all 6 of the different arrangements of the letters in the word cat.
If all the letters in the word phone are used, how many different 5-letter arrangements can be made beginning with a vowel?
So here's an example of a question where the implication here is that you can't repeat those letters. It's not stated overtly, but because we're dealing with the letters in the word phone, the assumption here is that you can't repeat them. Now, there is a little restriction implied here. Okay? How many different 5-letter arrangements can be made beginning with a vowel? So we have to start with a vowel, and I want you to always start with restrictions. Always start answering these problems by identifying the restrictions. So there's 5 letters here, 1, 2, 3, 4, 5. Okay, so I'm going to start with my restriction here that I have to begin with a vowel. Well, there are 2 vowels in the word phone, so there's going to be 2 options for that first letter. Now again, that 2 represents 1 choice out of 2 options, okay? Now after I've chosen one of those, I've got 4 letters left over. I really don't care which one you choose. There's 4 options there. And then I need to pick another one. There's only 3 options left, and then another one, and then another one. And so when I multiply those all out, this will be the total number of ways that you can arrange the letters in the word phone, assuming that you have to start with a vowel. And when we do that, we get 48. Okay, and that's big enough that I'm not actually going to go through and do all of those. but we just got to believe that that is the number of options.
And now we'll introduce factorial notation.
So now you've seen enough examples here that you probably have noticed a little pattern of multiplication, even from the last two questions here. 3 times 2 times 1. And then in this last one here, 4 times 3 times 2 times 1. That pattern of multiplication, okay, where you start at a given number and then you multiply it through all of the values all the way down to 1, is called a factorial. Okay, essentially what a factorial is, okay, is you're given some sort of number here, and here's some examples of a bunch of them. You're given a number, and then every number below that becomes a factor of the value you're looking for. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. They're all factors of the number that we're looking for. That is a really, really common form of pattern of multiplication, I should say, when we're talking about these sorts of fundamental counting principle problems. So a couple things to note here. First of all, notice that 0 factorial is 1. Okay. Now, notice all the rest of these things stop when you get to 1. So it's kind of a bizarre thing to think about 0 factorial being 1 here. So one of the ways that you need to interpret this as a factorial here, okay, a factorial is the number of ways of arranging, let's say, n objects. So if you've got n objects, the number of ways that you would arrange that would be n factorial, whatever number n refers to here. Now, so for 7 factorial, think about how that works. You've got 7 options for the first position, and then you've got 6, and then 5, and 4, and so on till 1 here. So how does that work with 0? Well, actually, it's quite simple, and it's, in fact, in many ways, it's so obvious as to almost be hard to kind of catch. So I'm going to arrange all of the elephants I have in my hand. Yeah, there's no elephants in my hand. There's only one way to do that, and that's to do nothing. Okay, which is kind of weird, but at the same time, kind of obvious. But anyway, so there it is. But 0 factorial is 1. There's other reasons why 0 factorial has to be 1 that we'll look at later when it pops up. But there you go. Another thing that I want you to notice about factorials, and let's take a look at, for example, at 5 factorial. Okay, this is 5 times 4 times 3 times 2 times 1. So 5 factorial is the same as 5 times 4 times 3 times 2 factorial. Okay, because 2 factorial means 2 times 1. So that's what that 2 factorial would do. It would take us back to 1. This would be the same as 5 times 4 times 3 factorial. Okay, because 3 factorial would be 3 times 2 times 1. So this would be 5 times 4 times 3 times 2 times 1. 5 factorial. This is the same as 5 times 4 factorial. 5 times 4 times 3 times 2 times 1. So I just want you to understand how factorials work, because in a little while here we're going to start to manipulate them and whatnot, and you need to really get the sense of what's going on here, how this little pattern works here, and how it can be, you can build a factorial from a factorial here. Okay, so for right now, just get this pattern of multiplication. So 4 factorial is 4 times 3 times 2 times 1. All of the values from 4 down are factors, okay, hence the name factorial. And if you want a kind of a concrete way to think about what the significance is of it, 4 factorial is the number of ways of arranging 4 objects. Okay, so now let's take a look at some more examples.
In how many different ways can 5 cars and 4 different trucks be parked next to each other in a line if a car has to be in the first stall on the left and a truck has to be in the last stall on the right?
All right, so to answer this problem here, let's take a look at how many tasks have to be accomplished. First of all, I've got 9 different vehicles here, so there's 9 tasks to accomplish. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I'm gonna do this a couple of different ways, and so we're gonna move away from this in just a moment. But there's some restrictions here. First of all, the first stall on the left, there has to be a car there, and there are 5 options for that one. And then on the right, the last one here has to be a truck. And there are 4 different trucks to choose from here. So those are my 2 restrictions. I got to deal with those first. Now, from this point on, it doesn't really matter which ones you pick. So there were 9 vehicles total 2 of them have now been placed. So now I've got 7 to choose from. There are 7 options for here, and then 6, and then 5, and then 4, and then 3, and then 2, and then 1. Okay? Now, another way that we could have done this would be to have thought it through like this, with just 3 different tasks to accomplish here. First of all, a car up front, a truck at the back, and now instead of thinking of it as being the 7 different tasks inside there that I have to accomplish, I can think of the one task as being to arrange those 7 vehicles, and I can do that as 7 factorial. Okay, and remember, that means 7 times 6 all the way down to 1. This is the same as writing that out. And when you do that, by the way, the answer is there are 100,800 different ways that those vehicles can be parked like that. And isn't that amazing how large that number is, given the relatively small number of objects that we're organizing?
How many license plates can be formed with 3 letters followed by 3 numbers, or 3 different letters followed by 3 different numbers?
So for this first question here, in terms of the number of license plates we're coming up with, we've got 3 letters followed by 3 numbers. Now, when it's listed like this, and when we're talking about license plates, now I'm not grabbing these letters off of a word, I'm just grabbing letters here. I think it's pretty clear that repetition is allowed. So there are 6 different symbols here that I need to address. 3 letters followed by 3 numbers. Now there is a very common mistake that gets made here right away. You need to be really careful with this. How many letters are there in the alphabet? Well, there's 26. Okay, now if the group of people watching this, and again, I don't know who you are, but if you're like a standard group of people, there will be a significant portion of you that actually off the top of your head don't know that. Okay? I suspect if a question like this showed up in the exam, there'd be all sorts of singing, A, B, C, D, E, F, G. Okay, people will be going through that. A lot of times people's gut on this one, oddly enough, is 24. For one reason or another, 24 here. Now, the answer is 26. Now, we know that we can repeat them. And now the question is, how many digits are there? How many different digits can we put in those positions here? And the answer is there are 10. Sometimes people jump on the option 9, but you got to include 0 in that, right? So there's actually 10 options for the first one, and then 10 for the second, and 10 for the third. Now, multiplying that all out, you get a huge 17,576,000 different license plates. Now, let's take a look at a restriction here. What if we throw the restriction here that you're not allowed to repeat those? Now, it's not a restriction in terms of I got to figure out where do I have to start this, but it's just not something that would be natural with license plates here. So now we still have 26 options for the first one, but if you can't repeat that, okay, now think about how many options you don't have. Well, I can't use this one. That gives me only 25 left over. Here, for the third position, how many letters can I not use? Well, I can't use those 2. That just leaves me with 24 options. And that might seem like a weird way to think that through in terms of the number of letters you can't use, but there is method to my madness, and that's gonna show its head a little bit later here. Okay, once we start dealing with some different restrictions here. Once we move over and start talking about numbers, okay, there are 10 numbers here, and then there's 1 number that I can't use, so that leaves me with 9 options, and now there are 2 numbers that I can't use, and that leaves me with 8 options. When you multiply those all together, and again, we're multiplying because in order to have a license plate, I need all 6 of those. I need the first one and the second and the third and so on. That's going to leave me with 11,232,000 different license plates. And it's staggering to me, or I should say incredibly interesting, how quickly these numbers grow. Like that's huge. And notice the difference between them. Like that's a substantial drop by insisting that you can't repeat those symbols there. Pretty neat.
You are given a multiple choice test with 10 questions. There are 4 answers to each question. How many ways can you complete the test?
Okay, so this is a great question, and it's got some very predictable results here. a lot of times when we give out this question on a test or a quiz or whatever, and by the way, you can probably expect that to be coming, okay? That sort of question just comes up a lot of times here. What the most general response to this would be to say 10 times 4, but that is incorrect, okay? This is totally incorrect here because you got to remember what these numbers represent. This is, again, what I've been trying to kind of go over again and again here. The 10 here represents 10 options, okay? So 10 different options here, but how many choices are being made with that 10? Just one. That 4 represents 4 options, but how many options are being chosen again? Just one. So think about the way a quiz works. If you were handed a 10-question quiz, is it acceptable to just pick one question, one answer, and then hand it in? That's all you did? No, you'd have to do all 10 questions. So that's not the way this works here. What would normally have to do here, in order for you to complete the test here, you've got to complete all the questions, and there are 10. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 little subtasks that need to be completed here. How many options are there for each of these tasks? Well, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4. Okay? Or 4 to the 10. Okay, and so now we just go to our calculator here, 4 to the 10, and the number of different ways that you could, like if you were just randomly putting these things on there, looks to be 1,048,576 different ways that you could complete or fill in the multiple choice portion of that quiz.
How many 4-digit numbers are there if repetition is allowed, repetition is not allowed?
So now we've switched things up a little bit now, and we're talking about building numbers. Now this can be quite confusing for people because we're going to try to calculate the number of different numbers that have the properties outlined here, but that can be really hard to differentiate the two here. You know, that what I'm writing out here is not the number I'm creating, it's the number of different values that have that property that I'm creating here. And another thing here, when you're coming up, oops, sorry, I'm looking at the wrong question altogether. When you're looking up or trying to figure out the number of different numbers you can create here with these restrictions, you can assume, okay, you assume you can repeat digits. Okay, just like when we were working with the letters of a word, you assume that you can't repeat those letters. Okay, here you can assume that you can repeat the digits. That's something that we're expecting you to just know here as you go in. Now in this particular case, you're told here that repeats are allowed. Okay, but that's something you should just know as you go into it. Now we're going to create a 4-digit number. That means I have 4 different tasks to complete. Okay, I got to choose a number for the first digit, then one for the second, third, fourth here. Now I have 10 options for the digit normally. But how many options do you have for the first digit of a number? And the answer is it's not 10. There's one digit that you cannot start a number with. Now let's just think about that. What digit is it? Well, it's 0. Because if you've got the number 16, if you put a 0 up front, it just makes it look goofy. It doesn't do anything. Okay, it's still 16. It's just with a 0 up front here. So there is an implied restriction here. You cannot start a number with a digit 0. So that means there's only really 9 options here for the first digit. Now, because repeats are allowed though, now for the second digit, there is no such restriction. I've got 10 choices, and then I've got another 10 choices and another 10 choices, which means we've got 9,000 4-digit numbers. Possible, I suppose. Okay, I would say where repeats are allowed, but I don't even have to say that. Just there's 9,000 4-digit numbers. Over here, if we don't allow repeats, now this one leads to kind of a weird little result. You just got to follow the line of thinking. Let's start up here first. How many different digits could I use for the first position? Well, again, I cannot use 0, so that essentially takes me to 9 digits. Now, let's look at this digit right here. How many digits can I not use for this one? Well, there's only one digit I can't use, and that's whatever one I used here, because repeats are not allowed. So whatever one I used here, I cannot use it here. But that's the only one that I can't use. That means there are 9 digits I can choose from. How many digits can I not use here? Well, these two right here. I cannot use either one of those two. That leaves me with 8 options, and then I cannot use 3 for this one. I can't use the 3 that I used here, so 7. So now, just multiply this through in your calculator, and we get that there are 4,536 different numbers where the digit is not being repeated.
Using the letters from the word equation, determine the following number of arrangements if A. All the letters are used, B. 4 of the letters are used, C. 6 letters are used and the word must begin with a Q, D. 5 letters are used and a vowel must be at the front and a consonant at the back, and E. 3 letters are used and they must be all made up of consonants or all vowels.
All right. So how many ways can we arrange letters in the word equation if all the letters are used? Well, there are 8 letters in the word equation. And remember what we had said before, 8 factorial, when we write that down, that applies exactly to this kind of question. It's the number of ways you can organize 8 objects. And the answer is, when you go to your calculator, that's 4,320. And by the way, just so that you all know this, just because I want you to see this as well, let me show you on your calculator what you're doing here. To get 8 factorial, you'd press 8, okay? Then what you would do is you would press your math button right here, okay, which takes us to these menus. And what we want to do is we want to go to the probability menu, okay, because this is a tool that's used quite frequently, probability, and the factorial is option number 4. Okay, so then press enter, and there's your 40,320. Okay, now let's take a look at another one here. What if 4 of the letters are used? Okay, we're only using 4 of them. Now let's just think about this. We're only using 4. That's 1, 2, 3, 4. Okay, how many options do I have for the first one? Well, 8, and there's nothing that I couldn't use. For this one right here, I can't use the letter that I used up front here, because remember, with these things right here, you have to assume that you can't repeat. Okay, so you have to assume that repeats aren't allowed, so that means there's only 1 letter that I can't use there. Here, there would be 2 that I couldn't use, and then here, there would be 3 that I couldn't use. And then we would just go to the calculator, 8 times 7 times 6 times 5. And we get that there are 1,680 different 4-letter arrangements of the letters in the word equation. So now in this case right here, we're going to use 6 of the letters, but we got to begin with Q. So we've got 6 tasks to accomplish, but we got to begin with the Q. And how many different options do we then have for the first position here? Well, the answer is there's only 1 option. Okay, of the 8 letters I could use, 7 of them I'm not allowed to use up here. Now, once that choice has been made, though, you can't repeat the letters, so now I've got 7 options for here, and then 6, and then 5, and then 4, and then 3. So then we go to our calculator, and we just multiply that out, 7 times 6 times 5 times 4 times 3, and that becomes 2,520 different 6-letter arrangements that begin with a Q. Okay, what about 5 letters are used, and a vowel must be at the front and a consonant at the back? Okay, so 5 letters here. 1, 2, 3, 4, 5. Those are my 5 subtasks here. I got to put a vowel up front. Well, how many vowels are there in equation? Looks like there's 5. So that means, again, I got to start with the restrictions. There's 5 options here, and that means there are 3 options for the last letter, which has got to be a consonant. Okay, so 5 options here, 3 options here. Now, there were 8 letters in the word equation. I can't repeat, so now that leaves me here. How many can't go here? Well, 2. Those 2 right there, I can't repeat that, so there's only 6 options here. For here, there are 3 letters it can't be, so it's got to be 5 here, and then this would be 4 options. And so now you just go to your calculator, 5 times 6 times 5 times 4 times 3, and there's 1,800 different arrangements that kind of follow that pattern there. This next one, what about 3 letters are used and they must be made of all consonants or all vowels? So 3 letters are used, but they got to be all consonants or all vowels. Now, let's just think about that. There's no way you can do those together in the same word. You can't have a word that's at the same time simultaneously all consonants and all vowels. So these are 2 very separate events that we're that we're identifying here. That word or, okay, is important. Like we were talking about before with the word and, or implies something here. And we want to make it clear here that or, sorry, I was gonna write something totally off topic there. Or basically implies addition. We have got two separate events, okay? It can happen in two different ways here, but I got to treat them separately. Now, this could be consonant and consonant and consonant, in which case there are three choices for the first letter, and then you've got two, and then you've got one, because there were only three consonants there. Or it could be all vowels, in which case I've got five choices for the first one, and then I've only got four, and then I've only got three. Okay? And so altogether, okay, this is going to be 6, this is going to be 60, so there will be 66 different three-letter arrangements that are either all consonants or all vowels.
How many three-digit numbers can be formed from the following digits, 2, 3, 6, 7, 8, if A, repetition is allowed, B, repetition is not allowed, C, how many three-digit odd numbers are possible if repetition is not allowed, D, how many three-digit even numbers are possible if repetition is not allowed?
So here we go. This first one says, if repetition is allowed. Now that's almost not necessary to say. We could have simply said without restrictions here. We have got 1, 2, 3, 4, 5 different digits to choose from, and we're only going to create a three-digit number. So there's 5 options for the first one. There's no restrictions here. I'm sorry. Yeah, sorry. Repetition is allowed, which means there are 5 options for the next one, and then 5 for the next one here. Okay, which means that's 125 different numbers that could be created with those 5 digits. Now, repetition is not allowed, and if that's the intention, again, you have to state that here. But again, there's no restrictions for the first digit, so that's 5, and then 4, and then 3, because the only one that this second one can't be is whatever the first one is, and the only there are 2 that this one can't be. It can't be what those first 2 are. And altogether, that's 60 different numbers, okay, that you can create that do not repeat the digits here. Now, how many three-digit odd numbers, if repeats are not allowed? So they have to state that. So 1, 2, 3. Now, if it's an odd number here, let's think about what it means to be an odd number. Okay, to be an odd number simply means that the final digit is odd. They don't all have to be odd. I know sometimes people, when you start to ask them questions like this, I've watched all sorts of people make the assumption that, oh, okay, that means all the digits have to be odd, and that's just not true. So what we need to do here is just focus on that last digit. Now, so how many three-digit odd numbers if repeats are allowed to? So how many odd digits do we have here? Well, there was 2, 3, 6, 7, and 8. There were just the 2 digits that would make this odd. Now, once that choice has been made, okay, whatever my first digit is, it can't be what this last one was. So out of the 5, that means I've only got 4 left over. And then for filling this middle digit, well, there are 3 options. It can't be either one of those 2. And so now, altogether, that means there are 24. Okay, there are a total of 24 different numbers that we could create here. Okay, this time, how many three-digit even numbers? Okay, whoops, numbers repeated twice here. If repeats, again, are not allowed. Now, there's 2 ways we could do this. But we'll do, for right now, we'll do it exactly the way we did it this way. Okay. We've got, how many digits have we got here that could be even? Well, there are 3 digits, the 2, the 6, or the 8. Okay, either of those, any of those could be used to finish an even number. That leaves us with 4 to start with, and then 3 in the middle here. Okay, and now that's going to be 36 different numbers, and I multiply that together. That's one way of doing this. Or, what we could do here is we could be a little bit more clever. We could take the total, and we just figured out here that if you don't allow repetition here, there are 60 numbers total. Okay, well, let's talk about this. So there's the total, and we've got 60 there. And then what we're going to do is we're going to subtract from that the opposite. And because we just did that. What's the opposite of even? Odd. So there we go. So how many odd numbers are there? There's 24. So if you take the total, subtract the thing you're not looking for, then what you're left with will be the thing that you're looking for. And there are 36 when you subtract 24 from 60. There you go. Two different ways of doing that problem.
How many 4-digit odd numbers are there if repetition is not allowed?
So we've got 4 tasks or subtasks to complete here. 1, 2, 3, 4. I've got to choose those digits. Now, again, our focus is going to be on this last digit here. How many options do we have for that last digit if we want to make it odd? Well, it could be 1, 3, 5, 7, or 9. There's 5 different digits that could be. That takes care of the number being odd. Now come up front here. I'm not allowed to repeat the digits, which means I got to think, how many numbers can I not use up front? Well, I can't use this one. Okay, whatever I chose there, whatever number that ended up being, I can't use that one. But I also can't use 0 here. Okay, I can't use 0, which means there are 2 digits I can't use. That only leaves me 8 left over that I can use. Now, how many digits am I not allowed to use here? Well, I can't use this one. 0 is not an issue anymore. I can put a 0 there, but I can't use this one. So now the only 2 that I can't use are these 2 right here. So again, that gives me 8 options for that second position. How many how many letters can I how many numbers can I not use for this position? Well, I can't use the ones that I've used in any of these 3 positions, so that leaves me with 7 options total for that position. So this is 8 times 8 times 7 times 5, which gives me 2,240 different odd numbers that don't have repetition. 2,240 different 4-digit odd numbers that don't repeat any of the digits. That's what we're looking for. I hope this makes sense here. You got to start with that odd restriction, which takes away one of the digits. Can't use 0 up front, so that takes away another digit. So there's why there's 8 options here. When we move into here, it's these 2 digits I can't use. Okay, because 0 is no longer that issue there. Hope that makes sense.
How many 7-digit phone numbers can be formed with the following restrictions? The first number must be either a 4, 6, or 9. The second and third number must match each other. The last digit can be anything from 1 to 5.
All right, well, this question is interesting just because of the number of restrictions that it seems to have here. So we've got a 7-digit phone number, so 1, 2, 3, 4, 5, 6, 7. So I've got 7 subtasks to complete here. Okay, so the first number here has to be either a 4, a 6, or a 9. That gives me 3 options for that first position. Now remember that 3 does not mean I'm putting 3 numbers there. It's one number from a group of 3 that I can choose. The second and the third number, all we're told is that they have to match each other. Okay, well, how many options do I have for that second digit then? Well, there's no restriction on what this one could be. There are 10 options there, but as soon as you've chosen this one, there's now no longer an option for this one. There's only one thing it could be. It has to be the same as that second digit. The next restriction says that the last one has to be anything from 1 to 5. Now that takes us way back here, and that means there are 5 options to choose from. Now, what do I do with these remaining 3? There's no restriction mentioned, so I have to assume that that's because there's no restriction there. So this could be 10 different digits, this could be 10, and this could be 10. And so altogether, that's going to be 150,000 different telephone numbers that you could come up with.
How many ways are there of getting from A to C, passing through each point at most once?
All right, so we've got a kind of a pathway problem here. These are little lines here representative of paths. So we're going to starting at A, and looks like we're going to end up at B, and then we're going to go from B to C here. Now, basically what I got to do here is I got to go from A to B, and then from B to C. So there's 2 little subtasks to complete the whole thing. First of all, I got to go from A to B. And there are 1, 2, 3, 4, 5 different line segments that I can use as options, as an option here to get through here. Now once I'm here, to go from B to C, I've got 3 different line segments that I can use to get from B to C. So there's 3 different options there, which means altogether, multiplying that out, there would be 15 different paths. Now that makes total sense. If I go from here, A to B, using this top one here, then there is 1, 2, 3 different ways I could then finish it. If I take this one, there could be 1, 2, 3 different ways that I could finish it off there, and so on. So yeah, 15 makes perfect sense there. So there you go, just some examples of the fundamental counting principle. And again, just to summarize here what we've looked at, we're breaking each task down into subtasks. The number here represents the number of ways of accomplishing that task, but you're only choosing one. That number by itself represents the number of options, but you're only making one choice in any given situation here. We also looked at factorials and what that little exclamation mark means, and you've seen some examples of where that pops into this particular topic.